Hi, welcome all of you. So today we are going to start the our 11th session on the one and two dimensional NMR spectroscopy for the chemist. And today we'll look for some problems on the what are the NMR spectra look like, especially the one dimensional and the two dimensional NMR spectra. Also, we'll see some example of the DPT experiment. So how the DPT spectra looks like and what are their importance in the day-to-day life of the chemist. So before going to the session, does anyone have any question regarding the what are the problems that what are the topics which are covered in the session in the week 11 of this course?
Sir, I have a different question apart from week 11.
Yeah, you can please ask. No, you can ask.
Sir, I need to ask what is the effect of temperature on the NMR?
Right. So NMR, temperature does have some effect on the NMR spectra. So if you look at the NMR spectra, temperature dependent NMR spectra of any solvent. So let's take the example of the uh, example of, let's say, CDCl3 or water peak by with the temperature. I will show on spectra here. Here I have just taken one example. Right. So here is the NMR spectra of the one of the peak, and it is taken at different temperature. So here, let's say it started from the 380 Kelvin and to 80 Kelvin. So that is the lower temperature. But if you look at the NMR spectra of this signal, this is any, I'm not sure for what exact signal this is the NMR spectra. But if you look at the spectra at higher temperature, it looks like it is a singlet. But if you try to decrease the temperature, we will observe some sort of the multiplicity or a broad spectra. Even eventually, in many cases, uh, we can able to observe the multiplicity. Here also, if you look at the spectra we got at the 80 Kelvin, it is a kind of multiplet. It is not like a broad singlet. It is a multiplet. There are small hump. If you zoom the spectra, we will observe the multiplet patterns hidden inside this signal. So it has the in terms of multiplicity, it does have the has the effect. Also, if you the first is the multiplicity. Multiplicity is different at different temperature, but not that much here. If you look at the from 380 Kelvin to 370, there is not a significant difference. But from 380 to 80 Kelvin, there is these two signals are completely different. So this is like a singlet, and another at 80 Kelvin, which will be looks like a multiplet. Here we observe there is a broad peak, but it is due to the merging of the multiple peaks. It's kind of multiplates. Also, if you look at the temperature, in some spectra, like the peak due to the OH bond in the water of the water molecule, that spectra also with the temperature, we observe slight shift in the spectra. I will just show the spectra of the CDCl3 at different temperature. So CDCl, not CDCl3, chloroform in the different temperature. So here is the Right. So this is the spectra. Are you able to? Sorry, I have shared screen. Right. So this is the spectra of one of the molecule, and which has taken at different temperature and moving from the 295 Kelvin to 380 Kelvin. We can here clearly observe there is slightly decrease in the peak position from lower temperature to higher temperature. So this is what the effect of the temperature on the NMR spectra. That's why whenever we are recording the NMR spectra, the NMR instrument is kept in the such room where there is a proper balance of the temperature. So generally, we keep the NMR instrument in a AC. We set multiple ACs at the same temperature, so as the room will have the constant temperature, and our spectra will not get affected. So yes, the temperature has effect on the NMR spectra. In terms of multiplicity get changed. Also, the peak position also can change with the different temperatures. So hope you can able to found if you just search you will also find there are another what are the remaining other parameters that also can change with the increasing or decreasing the temperature. So yes, it has effect. Temperature has significant effect on the NMR spectra. All
Okay,
right.
sir. I have another
Yeah.
question, sir.
Yes, please.
Sir, can we use temperature to study different isomer? For say cis and I have to study cis and trans isomer. So can we use NMR at
Yes.
different temperature?
Yes. There is one technique by which in which we generally keep our NMR sample. I mean, we can decrease the sample temperature or increase the sample temperature, and we can record the temperature at NMR spectra at different temperature. So yes, we can able to study. I mean, yes, people do study the different isomers, cis trans isomer, that sort of, and we check let's take example of steel beam. So steel beam, what happens? Uh, Steel beam like isomers, they at room temperature they flip from one isomer to another isomer, right? In the visible light or any if you just on the daylight also. But if you record the spectra at lower temperature, we'll get the different proportion of the cis and trans isomer. I mean, at lower temperature, generally the whichever the isomer is stable, we got the we can able to find out the disproportion in the amount of the one isomer than other. So yes, we can able to record this.
Okay, thank you, sir.
Yeah. Yeah, because many people do the same. There is special kind of setup to record the NMR spectra at lower temperature. We just throw the sample in the liquid nitrogen, and there is some sort of assembly while loading the sample. I'm not exactly sure what kind of how they put the sample in the instrument, but yes, there is there if you as I'm in IIT Delhi also there are some groups they record the spectra at different temperatures. So yes, we can do that one and able to find the proportion or disproportion of the isomers. All right. Anything else?
No, sir, not yet.
All right. So, in last lecture, we have seen there are multiple techniques that able assist us to find out the and identify the structure of the molecule. So, in last lecture, I have shown how this I have used this one uh, proton 1H NMR as well as the cozy NMR spectra, and I have assigned this NMR uh, signals from the compound and able to characterize this full spectra of this molecule. If you look at here, all hydrogens are here in the spectra are assigned here. So let's if you see here, so this multiplied at 7.58 to 7.5 is due to two hydrogens which comes from the benzothiazole. Also here also if you look at here this doublet at 7.23 hertz, 7.3 ppm, which show the J as a 8.5 hertz. This doublet of the two hydrogen is comes from this phenyl hydrogen. This phenyl hydrogen of this green part as I have shown here, and which I have characterized from the which I have confirmed from the this 2D NMR spectra. So here is the doublet of the one the orthoproton of this OH. Then again, there is one another doublet with the doublet of doublet with the one J value is about 8.5 and another J value for this one was about 2 hertz, and that is it has some meta coupling, right? That's 2 hertz means. So here this doublet comes from the hydrogen which is at ortho position, sorry, the meta position of this OH. And again, this couples with the, if you look at here, this couples with the another doublet with the very small coupling, sorry, the splitting constant J value about 2.5 hertz, and it comes from this hydrogen which is at isolated hydrogen which is sits here in between these two functional groups, right? So by using this 2D NMR spectra, we can able to characterize our structure fully and assign each and every peak from the NMR spectra which correspond to which proton in the. And here are the NMR data that I have written. You can able to see here. I have already uploaded the slides in the previous one. Also, next I have added some another example of this another similar molecule which has the alkyl chains as well as this one. And in last time I forgot to mention these 2D NMR spectra I have shown only from this 7 hertz, sorry, 7 ppm to 8.4. If you look at here, it is 7 to 8.5 or 8.4 ppm. So I have taken only aromatic region because in the aliphatic region there is only the alkyl chains. That so I have just zoom in and just show the whichever the much needed part to assign. I mean important part required for the assigning the each and every signal. So this is from the 7 to 8.5 ppm. The remaining spectra is in the alkyl region that I have just cut it out and I have just shown this zoom spectra. Further, I have uploaded some other also spectra for let's say this molecule. This molecule contains the benzothiazole ring, another phenyl ring. Here the phenyl, and again the phenyl ring with the AA, sorry, AB type of coupling spin right here. If you look at here, this is AB system, and that we have already seen how the AB, AX, that kind of system we label for these aromatic signals. And this is the carbazole. So for this molecule, I have taken the 1H NMR spectra that I have shown here, 13C, which this is how the 13C spectra for this material looks like. There is no any signal in the aliphatic region. Also, there are multiple signals. If you count the number of signals here and this one, this will uh, this molecule shows this many number of signals in the aromatic region. And moving to the 2D, the cozy NMR spectra of this molecule. So this is how this cozy NMR spectra looks like. So I have just in the similar manner identify one of the signal. So in this case, I have started from uh, this doublet which is here. So which is the significant doublet in the same benzothiazole case as prior. So that it has the same sort of coupling. This is doublet. Another here is doublet of doublet, and further here is doublet with a very small coupling constant with a 2.5 hertz J value. So this green line is green lines. They signals correspond to this phenyl ring. Also, this red line signals correspond to the benzothiazole, and this purple, the purple one that I have shown here. If you look at here, so this is the due to the purple that sharp doublets, right? And again, there are some signal due to the carbazole, which I have indicated in the blue line. So you can able to you can see this and analyze the spectra when I upload it on the Google Drive. So here is the data for this one also I have written. So moving to the next hour, I would like to show another type of the spectra that is like DPT type of experiment, right? We know we take the carbon NMR spectra. So also, does the carbon belongs to the CH? Carbon is a part of CH3 group or CH2 or CH or it is a quaternary carbon. So to distinguish that type of carbon, we use the DPT type of experiment. So DPT stands for distortionless enhancement by polarization method, and it was induced that give the information about the neighboring hydrogens which are bound to the carbon, right? So, and if you look at the short summary of this one, how this DPT gives the signal. So in carbon NMR spectra, if we took the carbon NMR spectra, we get the signal due to the carbon, and all carbon, that is quaternary, primary, secondary, tertiary, all type of carbons are shown in the 13C NMR spectra, right? And in the DPT 45, what happens in the DPT 45? We got the signal due to all carbons except the quaternary one. So this is due to the DPT 45, right? So this is how the DPT 45 experiment looks like. So you just record the carbon 30 and etc. In the same one, we can give the command for DPT 45. So we observe there is no, we can able to distinguish the quaternary carbon in this one. So the signal is shown in the carbon but absent in the DPT 45. It means that signal is correspond to the quaternary carbon. Again, if you record the DPT 90, from the DPT 90, we can able to distinguish between in the DPT 90, we observe the signal due to the primary CH. So if you have the CH, that type of carbon, only one hydrogen attached to the carbon, it will shown in uh, the spectra. It doesn't matter whether it belongs to the aliphatic region or aromatic region, but the carbon which has the only one bonded hydrogen, so which will shown in the DPT 90 spectra. And further, if you record the DPT 135. In the DPT 135, what happens? We will not get any signal due to the quaternary carbon, and we get the positive signal, that is in the positive direction, in phase signal due to the CH, also in phase signal due to the CH3. But we get these are in the positive direction, and in the negative phase or anti-phase, we get the signal due to the CH2 group. So by this way, we can able to distinguish the CH2, which is the CH2 and which is the CH3 by the combination of all these three spectra, three type of DPT experiment. So let's take the example of one of the molecule. So this is the one of the very prominent example, uh, often shown to explain what is the use of the DPT experiment. So we have the carbon spectra. Here is the carbon 13 spectra. This is the just like sorry. So this is the 13C spectra of this 13C spectra of this molecule. So in the 13C spectra, what happened? We got all the signals, right? This signal is due to the CDCl3. So for now, ignore this signal, right? And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have the 10 signals in the 13C NMR spectra, right? Now we have to identify which signal belongs to which carbon. So we have, if you look at the structure here, we have 1, 2, 3, 4. 4 carbon which are like olefinic carbon. And among that, here it is, this is the carbon attached to the two hydrogens, right? And also another carbon which attached to the two hydrogens. So we have two uh, carbons in the olefinic region. So olefin, it means it's around the 100 to 120, that sort of, right? So here, if you look at here, there is two signals and which is in the range of 100 to 120. So we can able to easily distinguish, yes, this carbon should come in the olefinic region. So if you look at here in the olefinic region, there are two signal, and if you record the DPT 135, we observe this two CH2 comes in the negative direction or in the antiphase in the DPT 135. So it indicate these two CH2 belong to the this olefinic carbon 8 and 10, right? And also in the if we look at the spectra here, let's take this one, this signal in the aromatic region also. So what are the remaining signals here in the DPT 135? As we have seen earlier, we 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 can observe the here DPT 135 will not observe any signal due to the quaternary, right? So for the quaternary, we will not get any signal in DPT 135. So let's comes back to the example. So which signal is absent in the DPT 135? So if you look at here, here there is one quaternary carbon, 6, right? So this 6 carbon. So here in this one, there is one signal which is absent. Here there should be one signal, but it is absent. What does it indicate? It belong to the So it is a quaternary carbon, right? So this signal is absent that I have shown here in the green one. So this signal is absent. So this is the signal. So this signal is belongs to the carbon number 6, which is a quaternary carbon. Again, if you look at, there is one another signal at around 138, which is due to the which is in the again in the olefinic or aromatic region, right? And which definitely belongs to the 1CH, right? So here the carbon 7. So this signal is due to the 7 number. So I will just label this due to 7. Another, we have identified this signal is due to the 6. This signal is due to the in aromatic region, right? This signal is due to the 7, right? Again, these two signals is due to the 10 and 8. So in this one, so this is due to the 8 and 10. So not sure which is which, but among these two, this is the signal due to the this CH2, terminal CH2 of this olefin. Again, if you look at in the aliphatic region here, around 68 ppm, there is signal shown in the positive direction. What does it indicate? It might be due to the CH or CH3, right? So this is definitely due to the CH. Which CH? So there is another. So here there is one CH. Here is also another CH. Sorry, this is a here also one CH there should be, right? And here also one CH. So this signal is belong to which CH among these two. So here it is still it has we assign remaining signal, then we come back to this signal. So here there is three signals in the uh, near 20 ppm, right? These three signals is all three in the positive direction, right? So it indicate it might be CH or CH3, and also this is due to the CH. But among this CH, the CH which attached to the electron withdrawing group, right? Because if you look at this one, it is around 68. So definitely this CH that is 4, right? The carbon number 4, this will be the definitely the due to the carbon number 4. That is, it has the electron withdrawing group attached. This is the OH group. It is electron withdrawing. So definitely it is due to this uh, the carbon number 4. And among this one, so there will be definitely two CH3 and one CH3 is remaining. Then we recorded the DPT-90. And in the DPT-19, what happens? As we earlier seen in the DPT-19, we can able to see only the CH, right? So if we go back to our example, so here in between that middle signal, right? Middle or this terminal, sorry, this terminal signal. So this one, if you just, this is, the scale is same for all this one. So definitely this is the signal, right? So this signal is due to the CH carbon. So this is definitely the CH attached to the 2 position. That is, sorry, the carbon number 2. So this signal due to the carbon number 2 and this remaining terminal 1 and 9. So this is this remaining to 1 and 9, 1 and 9. This is due to the second carbon. So this signal is due to the CH2. So among these two, there is one CH2 and this CH2. So obviously this is due to the 3. This is due to the 5, right? This is due to the 4. This is due to the 8 and 10. And here this is due to the 6. This is due to the 7. So in this way, you can able to assign each and every signal from this epsilon molecule. So by using only the 13C NMR spectra, 13C, DPT-90, DPT-135. By using these three spectra, we can able to assign each and every signal in this molecule. So this is one of the traditional example generally uh, uh, shown to explain the utilization of what is the use of these DPT spectra or DPT techniques. So to assign the carbon belongs to the which the signal belong to the which carbon. So this is another some example that I have taken from my data. And if you look at this molecule, it has some aromatic protons, right? So this aromatic proton, there are some terminal CH3 groups. So obviously this CH3 comes in this region. There is one CH group, so this belongs to the CH. I have taken only the DPT-135, and in the DPT-135, so whichever the CH2, so this is the only CH2 here in this compound, and which shows here in the negative direction, right? So we can able to assign the signal at the 46 ppm. This signal is due to the CH2 of this highlighted one in the green, right? So this is the use of the DPT experiment. So any doubt in this one? All right, if you don't have doubt, we'll just move to our problem. Some of the problem that I have from uh, the assignment I have taken as it is, and I will just go one by one quickly. So in the 2D experiment, the T1 and T2 periods are they are the evolution and detection. So yeah, so this is due to the evolution and detection. Another question is in the 2D cozy experiment, if the spin are not J coupled, then the cross peaks will be absent as there is no correlation. Next question here is the if the molecule contain three spin A, M, and X, the JAM is 10 hertz, JAX is equal to 0, that is uncoupled, right? And JMX is 8 hertz. The 2D cozy experiment gives correlation between. So in this one, as I have shown some example, right? So if you have some, so we have here, I have shown earlier. So this is the one of the system, the molecule I have, right? And here is one substitution, let's say any X substitution or just any substitution, right? Here also any substitution, another. And this is one hydrogen. This is another hydrogen. And this is the third hydrogen. So JAM. So there is this couples with coupling constant about 10 hertz, right? Then JAX. So A. So this is the A. This is the M. And this is X. But in this one, JA and X doesn't couple, right? So here it is written JAX uncoupled. Then another question here, another given JMX is 8 hertz. So here JMX, AJMX, here it is 8 hertz. So the 2D cozy experiment gives correlation between. So obviously it will give the correlation between uh, JAM. Also it will give the correlation between JMX. So JAM and JMX is the correct option here. So forget about this J coupling value. But if you look at the example here, uh, because the meta coupling is definitely not that much 8 hertz. It is if you look at some any example, the meta coupling is merely about the 3 to or maximum 2 hertz. So if you look at just I just make it here 2, then also in this type of system it will be the same option, the JAM spin and JMX spin, right? The next question here is the presence of only diagonal peaks in the 2D NMR spectra implies. What does it indicate? The presence of diagonal peak. It indicate the no scalar coupling among the spin and the spins are isolated. So if you look at here, the isolated spin in the I have in the shown the spectra that I have shown here. So if you're able to analyze which is the isolated spin here. So here I think yeah, this is the yeah, this is the best example to show here for this one. So if you look at this spectra and if you see this benzene ring in between, this is kind of A-B system, right? A-B system, right? And which is completely isolated from other. So for this purple, if you look at here, there is only diagonal peaks are present. So this is the only present. There is no any further coupling of this peak. So this is due to the isolated spin. And what it mentioned in the spectra, sorry, the question, the presence of only diagonal peaks in the 2D NMR spectra, which indicate the scalar coupling among the spins, and the spins are isolated. So in the same manner as in the example. Next question is, in the rectangular uh, 19 T1, 19 T2 Cozy experiment, the diagonal are in phase and the cross peaks are will be in the anti-phase. So in phase means it is in the positive direction, as I have shown in the DPT. The positive direction it indicate in phase, and the negative direction it indicate which is in the anti-phase here. That is DPT 90, right? Example of DPT 90. In the another question given, it is preferred to take the DQF Cozy spectrum, uh, isolated of Cozy spectrum, because in the DQF Cozy, the both the diagonal and the cross peaks are in antiphase dispersive. So this is the option. So antiphase dispersive is the option here for this. Another question here mentioned the role of spin lock pulse in the Toxi TOCSY experiment is uh, for isotropical mixing, where the spin lost their identity, and another one is the for the phase transfer of the magnetization among all the coupled spin system. So this 1 and 2 are the correct option for this one. In the eighth question, a molecule contains CH, CH2, CH3, and CO as a quaternary carbon in a one bond heteronuclear, that is 13C 1H coupling correlation spectrum. Few correlated peaks are missing. The missing peaks could from, obviously it will be from this quaternary, right? This CO and this quaternary carbon that I have shown in the DPT. So this, sorry, in the correlation spectra. I think I haven't shown the correlation spectra of the 1H13C, this one, but I have shown the correlation due to the 1H1H, that is the COSY. 1H1H I have shown example. Unfortunately, I don't have right now the example of this 13C 1H COSY. It is also the same. So in the one direction, there will be a 1D 1R spectra. Here, let's say this is the 1H NR spectra. In the another direction, there is a 13C NR spectra. And we will get the same diagonal peaks. And from that, we can able to identify the correlation between the protons and the carbon. So here, let's say here the signal at 5.2, there is a singlet, and also in the 13C there is signal at let's take example 85, right? 85 ppm. So this spectra will show here the dot. What does it indicate? It indicate this the signal in the 1H inner spectra at 5.2 is correspond to the signal at the top the in the 13C at 85 ppm. So it indicates this carbon and this hydrogen, they are attached to each other. So we can do this correlation using the 13C1H correlation spectroscopy. So here the answer is the CO and the carbonyl carbon and the quaternary carbon. In the next question, in the HSQC experiment, the advantage of over regular head core experiment because there is gain in the signal intensity. Also, I mean, sorry, in the HSQC experiment, the advantage over regular head core experiment is the gain in the signal intensity. Also, the experiment is faster compared to the HSQC experiment. So, sorry, compared to the head core experiment. So, HSQC definitely have these are two the advantages. Another one is the in the molecule CH3, CH2, CH2I, both 2JCH and 3JCH correlation are related. Then, in a decoupled 13C1H HMBC spectrum, each proton gives the correlation to the both the carbon that are 2 and 3 bond away. So this is the these are the some problems that these are the answers of the problems in the assignment. So hopefully you got the all the answers of to your assignment problems, right? So any doubt in the this one dimensional and two dimensional NMR spectroscopy? All right, I will just stop recording.